Okay, so continuing on with section 2.3, so we're talking about domain and range of all types of equations. And in the last segment, we talked about how that the two kind of what I would call troublemakers, the two troublemakers you'll experience are the radicals and the fractions. So those are the two will have really special domain and range to watch, although they all, you can analyze, but those are the two that will come up mostly in your assignments. All right, so I've got an example I want to continue on with you. And here's 3 examples where we're finding the domain and range, kind of typical problems that we would be asked to address. So for the first one, I want you to think about domain and range, and all of these are functions, by the way, so we can go ahead and answer that. No x is ever repeated, so they're all functions, but what are their domain and range? So you may want to pause the video, take some time, pause, and try those 3 based on what we did in the last section to quiz yourself. All right, I'm going to go ahead and proceed though, but hopefully you're kind of using that strategy with the videos that you'll pause, work some things, or rewind and listen again. And if there's anything you feel like you need an extra video of, also I hope you'll send me an email and reach out to me. I can always try to do that for you. All right, so the first one is a linear because x is the first, y is the first. I know that to graph to be a line. We could plot some points like the xy table and find that it is a linear equation. It looks something about like that. So what we learned on the previous is for lines, the domain and range is all infinities. It opens left and right. It keeps going left. It keeps going right. It's more distinctly looks like up and down, but as it goes up, it's also moving right, and as it goes down, it's also edging left. So left and right, it never quits. There's no restrictions on how far it's going to go as it keeps, if we had a bigger graph paper, we could show it. It keeps on going down. It's going to eventually wind up way out there somewhere, way over there. So lines are always these infinities for the domain and range. They never stop going wide or tall and low. All right, the troublemakers, like I mentioned, are these 2 guys. The square root function, because you cannot put something in for x that makes it imaginary. Remember, domain means what can I plug in for x that gives me a real answer for y. So if I were doing a t-table of values, for example, and I try to plug in 0, when you plug in 0, 2 times 0 minus 5 is the square root of negative 5. We know that square roots of negatives are imaginary, so not real, so it's not in the domain. We say 0 is not in the domain. So what is in the domain? The quickest way to figure that out in the radicals is you say whatever's under the radical has to be greater than or equal to 0. Keeping it positive. It's allowed to be 0, but 0 or larger. So like this. We can throw the 5 across the line and divide by 2 and find out the first allowable value in the domain is 5 over 2, or 2.5. That's the first allowable value that you can plug in and get a real answer for y. So we'll say the domain, the x values, start and include 5 over 2, and then anything larger than that, so to positive infinity. The range, the smallest value that you're getting there when you plug in 5 over 2 will be 0. So the smallest value for the range or for y, it starts at 0. All right, next one, the fraction function. So the deal with that is if you put in a number for x, which is going to be negative 2, can you see if you plug in negative 2 plus 2, you get a 0 denominator, which is a big no-no in math. If you try dividing by 0, it is undefined. It doesn't even make the math list of things. It's not imaginary. It's just nothing in math. It's undefined. So the way I know that, you could say what makes x plus 2 equals 0. That's the value I cannot have. Throwing the 2 across the line tells you when x is negative 2, you're in trouble. You cannot use that value. Anything else is okay. You can plug in, and you take time to make your t-table, and you could develop this idea by testing different values. Everything else is okay. This is the only problem for this fraction thing. You cannot plug in negative 2. So the way we write that is we say negative infinity up to negative 2. We put a parenthesis to say I'm not going to touch negative 2 or include it. The parenthesis excludes that endpoint, but just up next to it. Then union, we pick up on the other side of negative 2 and go to positive infinity. So that's how we write out our domain. This means excluding negative 2. For the range, The value for the range, you cannot achieve 0 because there's a constant in this fraction. 9 divided by something is always going to give you a value other than 0. You know, to get y to equal 0 here, you would need 0 divided by stuff, right? 0 on top, 0 divided by anything is 0. It's 0 on the bottom that's the problem. So if you could have a 0 on the top divided by anything, that would be 0, but we can't because 9 is there. 9 is a constant, and its constants don't change. You know, there's no x variable to plug in for it, so it's just constantly 9. So you cannot achieve 0 for the answer for y. So the range never touches 0. So we write that as negative infinity to 0. That's our excluding 0 idea. All right, so that's domain and range. The rest of this section talks about using the function notation. So I'm going to move into that thought with you on example, example 6. So instead of calling these things y equals, these examples I just had here, I could say f of x equals. F of x is the function notation. It means the same thing as y equals. F of x and y are interchangeable. So why do it, you might say? And that's because it tells us that something's passed the function test. We don't have to wonder, is the vertical line test working? It's already been stated. If it's f of x equals, then they're saying, yes, this thing, no x is repeated, you're safe to assume it's a function. Secondly, it's a naming, a more specific naming. F is the generic one, but we could also have like a g of x equals, or an h. That's what seems to be the letters they like in this section, but it could be any letter. R of x or m of x, whatever your name is, it's a naming. So this tells me, look at function f, or look at function g. It's a naming, so when you use the different letters. So for example, on example 6, we've got some we can use here. We've got f of x equals this function, negative x squared plus 5x minus 3. Then we have a separate function, g of x, that is 2x plus 3. So now we can do various operations with those two functions. If I say, hey, look at function g, you know it's this one. If I say, look at function f, it's the first one. So here's what they ask us to do in example A. It says find f of 2. So f of 2 means go to function f, this expression, and instead of having f of x, now it's f of 2. That means make these 2's. Change your x, what would have been f of x, change your x's to 2's. So that means this would be negative 2 squared plus 5 times 2 minus 3. And now I have an arithmetic problem. You can use your calculator to do that. That negative is not in a parenthesis, so that is negative 4, 10, and minus 3. Let's see, I think that comes out to be an answer of 3. So f of 2 equals 3, we would say. All right, on example B, they tell us to do something different, f of q. So whatever it says in this parenthesis is what you plug in for the x. If it says plug in f of 3, we plug in 3. F of 7, we plug in a 7 and work it out. Or it could give you an algebra problem to plug in, like here, plug in f of q. So we plug q in for the x's. I know it seems like a weird thing to do, but it's what it says to do, so there we go. So when I plug in q instead of x's, now it's got q's in the problem. Now this I can't work out because there's nothing I can do to that. I don't know the value of q like I did up here, and there's no algebra to reduce it, so that's just what I do. Okay, example C. C says do g, so we're move to the other one, g of a plus 1. So that means look at function g, which is 2x plus 3 defined as, and it says instead of having x, make that an a plus 1. So again, whatever's in this parenthesis, you go to that function and plug that in. So we're going to say that x is now 2 times a plus 1 plus 3. Plugging in this for the x. And now this I do have a little something I can do. I know to distribute, so we could reduce that a little bit. And then combine any like terms. So I could do a little manipulating there and reduce it. And then that would be a reduced answer. All right, let me give you a couple of you tries on this. Let me get you some new values. Let's say we have a function f, and that is, let's say, x squared minus 6x plus 2. Let's have a function g that is 2x minus 1. And let's go function h that is, let's see, what can we do? X squared minus 3. All right, so let's say I ask you to do f of 1. On b, let's do g of 3. And on c, let's do h of a. And let's do one more, h of a plus 1. All right, you can pause the video if you like then and work on these examples. But I'm going to go ahead and proceed. So the answer would be f of 1 means look at function f and plug in 1s. Whatever it says in this parenthesis, you plug in. So 1 squared minus 6 times 1 plus 2. And that's arithmetic that I can just work out either on my calculator or by hand. And let's see, what is that? Negative 3 is what I'm getting for that. The next one, g of 3, function g I've defined as 2x minus 1. So I'll plug a 3 in for the x. That makes 2 times 3 minus 1, or 6 minus 1, 5 for that. Then I went a little more algebra on you. So we can plug in numbers, and then that's nicer because then we can just kind of do our calculator thing on those. Or they can tell us to plug in some algebra. So whatever's in this parenthesis, you plug it in for that value. So now it's going to be a squared minus 3. There's nothing to do to that. I don't know have any way to simplify it. So that's just it. But on the last one, plugging in a plus 1 for this x, again it's function h, so it's this bottom one. I'm going to make that x into a plus 1. Now notice it is squared and then minus 3. So this I do need to simplify. I can square that. A plus 1 squared means a plus 1 times a plus 1. And so that could be FOILed out, and it will give you an a squared, 2a, and a plus 1 when you combine your middle terms, and then minus 3 to incorporate for a final answer of a squared, 2a, and minus 2. So that's what you should have got. So hopefully you made it to that final answer. All right. Let's see. Oh, another thing to mention is sometimes instead of showing you the equation, you might have a graph of a function. Like it might show you, let me draw a little graph quickly for you. Maybe we have a picture instead of the equation written out. Maybe it's drawn out as a picture. And they say, hey, here's function f. There's f of x. So now find, let's say, f of 0. So what does that mean if you have the picture to do instead of an equation to plug in? If we had the equation, we'd plug 0 in for x, but instead we have the picture of the solutions. You know, graph, it would be a picture of all the answers to it. So it's almost like a cheat sheet here because it's already worked out. So when we plug in 0 for x, you know, this is our x-axis. Here's x is 0. What is the y answer? If you had the equation and you plugged in 0 for x, you would have got 1 for y. But here we have the graph, so it's got the answers graphed out for us. So again, this means plug that in for x, so go on the x-axis to 0 and see where it hits the picture, the graph, it hits it at 1. So we say f of 0 is 1. Another example, let's say it said do f of 1. So again, that means x is 1. Here's x is 1. 1, 2. How high up is it? At x is 1, it has a y value 2 places up. So we say f of 1 is 2. So that's the idea when you have the graph. And then the last thing in this section talks about increasing, decreasing, and constant function. So really it's saying when it's increasing, this is an increasing slope. We're looking for where the graph has a positive slope. And then decreasing would be where it's a negative slope. If it's going this way, that's a negative slope. And then constant slopes are where it's a 0 slope, a flat line. So the last little example, you may want to just look at that in your book for further directions, but it's all about the slope of the line. Again, when you read a graph from left to right,